Next on will be Tin Ferkovic, an ML researcher at DSC. Tin Ferkovic is a final year master's student in data science at the Faculty of Electrical Engineering and Computing. He has been studying NLP for the past 3 years under the mentorship of Jan Schneider. This talk will explore the concepts of a general approach to multitask learning in transformer-based architecture, novel adapter-based and hypernetwork techniques, and solutions to task sampling and balancing problems. Sretno.
As mentioned, this will be about multitask learning. We'll focus on transformer architectures, discriminative ones, not generative ones, so that it's accessible to everyone. And it might get a bit technical, but we'll not go into depth in any of the things, but we'll take a look at some of the architectures. So I am a final year data science student at FER, NLP researcher at DSC. And now to get right into it, this is the agenda. First, we will go over the standard approach of how single task learning is done, how probably something that was just mentioned previously is done, like single task learning, and then 3 approaches to multitask learning. First one will be a shared encoder, then we'll go over the adapters and finish up with hypernetworks. So the complexity might get higher as we go. So to start with, in 2018, BERT paper was released, and the idea was simple. Now it's simple. At that time, it was revolutionary. You get pre-trained weights, and you basically fine-tune them on the task, on the data set that you need. And then, okay, maybe you have one problem, and you come up with another problem, but what if you have 5, 10, 20 problems? What do you do this 20 times, you say 20 models. It comes with the scale, the problems also arrive. And I will take a look at some of the numbers, for example, for BERT large. If you want to just store the model in terms of parameters, you get 345 million, which comes down to 1.34 gigabytes of storage space. If we're talking about checkpoints, you need to also save the optimizer states. Let's say you're using Atom optimizer, so this comes up to 4 gigabytes. If we're talking about GPU memory, just to save the model and the optimizer state, it's 5.5 already, and we haven't even loaded the batches and everything. Just to get the feel of the scale, this is not something you would do, but for the pre-training, it was done with 64 TPUs for 4 days on an estimated cost of $7,000 US. And the CO2 emission, that's something people nowadays like to hear, it's like an average transatlantic flight. But this is today considered to be a small model. Today's generative models go up to 6,000 TPUs instead of 64. The training times go to 50 days instead of 4 days. And the estimated cost, if you were to train this by renting the TPUs to pre-train them, it would be $10 million US. But this is generative, and this becomes at some scale unsustainable for everyone, right? So what is the idea? We'll start with the simplest approach. Just instead of having n different models, you would share the encoder, and you would have task-specific heads. The idea is very simple, but we'll see what the problems are. So okay, you get a single model instead of n. You get n times storage reduction. Great. You also share some knowledge, which can be beneficial. It can be problematic because you're updating the same parameters, but it can be beneficial. Like that's at least the idea. To also benefit from other tasks, and also then it's more data efficient. You might need less data because you're also getting some gradient updates from other tasks. The architecture, very simple. One shared encoder in blue that's updated by all the tasks, and then task-specific heads, which you activate only when you are using that specific task. Right, but with this, when you're sharing so many weights, you you imagine that you need you have some problems, you have some decisions to make. So let's start with making the batches. Okay, so you can do it sequentially. I train on task A until conversions, then I go task B, task C. But this will lead to catastrophic forgetting, right? As soon as you start training task C, for example, you've already forgotten everything about task A. So not a good strategy. You can make homogeneous batches. So every time you take a batch, you will sample from one of the tasks. But we can do even better. We can do heterogeneous batches, which is basically the same as starting with the homogeneous batch, just one batch, one task. But then you accumulate the gradients over a few batches, and then you perform the optimal step, so that in one step you get multiple tasks, not just one. But we're not done with the decisions. Maybe we also have a problem of how do we sample. We can do simple strategies like proportional or random. But if you take this proportional, then you have very small data sets and very large data sets. And the large ones will eat out the small ones. They will take over the training. So it's not a good strategy. We can do it randomly by, for example, uniform sampling. But then you underfit on high resource data sets because they would usually get more gradient updates, but this time you're making them equal, like uniform. You can go a bit more sophisticated with temperature-based sampling. That comes for like thermodynamics. But the idea is that you start like proportional, you get the probabilities, but you tame them out a little bit. So the higher probabilities will go a bit down and the lower a bit up, depending on the temperature. You can change this temperature throughout the training. That's annealed sampling. You start like proportionally in the beginning and you move towards uniform sampling towards the end, so that as you're approaching this final state, you would sample the task equally. You could also use more sophisticated techniques like uncertainty, but now you're also prolonging the training time, because anytime you're choosing a batch, you also need to have some heuristics. Okay, how do I choose the batch? And it's basically win some, lose some. You need a lot of decisions to make. How will you weight the loss? Maybe some task doesn't have troubles converging, the other does have. You could use uncertainty. So you have your logit that the model has outputted, you have a ground truth, and maybe the larger the difference, maybe you sample this task more. You could use the learning speed. If it's converging slower, you give it more weight, right? If it performs worse, you again give it more weight, but maybe then you have one task that is regression, the other task that is classification. They have different losses. This is mean square error, this is binary cross entropy loss, and you need to take that also into account. Another thing that happens is you have a task with 2 labels, and you have another task with maybe 25 labels. The one with 25 labels would tend to have a higher loss because it chooses from a larger pool of labels. Then a good strategy is also to normalize it by dividing the pointillist by log n. So a whole bunch of decisions, a whole bunch of problems when you're sharing so many parameters. First of all, sharing so many parameters means that one task will pull the gradients to this side, the other one might pull them to this side, and they will cancel each other out. You did not get any benefits from this motivation, the idea of sharing the gradients, of knowledge sharing. You have troubles sampling. Okay, as I mentioned, you have more sophisticated methods, but they also take time. This heuristics takes time, it prolongs the training time. Maybe you could get away with something simpler, but you don't know if you don't try. It's a hard decision to make. In terms of performance, this generally underperforms the single task learning. So you use less resources, you use less storage, but you did not gain anything on performance. That's something that people maybe don't want to give away. As mentioned, low resource data sets, high resource data sets, a danger of underfitting or overfitting. It's hard to balance them out. Loss weighting, the same as sampling, more sophisticated methods, but yes, maybe you could get away with something simpler. And if you want to not have interference, which was the first point, that's the biggest problem here, you maybe want to group the tasks first. But that's a whole new step that you're introducing. Just before you even start training your models, you need to find the ones that are similar, that are compatible, So a lot of problems if you share so many parameters. That's why people came up with the idea of adapters. They're small, they're modular, and the whole concept is completely different. So it's like, okay, let's look at this in a different way. We will train as least as possible parameters. We will inject them into the architecture as intelligently as possible. And we'll not share anything compared to the shared encoder, which shared almost everything besides the star-specific heads. So that is the idea. Around 0.5% of trainable parameters, so 200 times less compared to single-task learning, while the performance stays on par. And the beauty of this is that they're modular. You can train them, you can save the weights, you can share the weights, somebody else can download it, plug it in, just use it for inference, maybe train it further, again, save and share the weights, and this is like distributed multitask learning. That's the whole concept. Because they're so small, you can share them easily, you don't have those problems. There's 3 types of compositions that you can do with adapters. Let's take a look at transformer as like a bunch of functions. And then you can do function composition. You can insert them like sub-functions into the transformer. You can do it like input composition. So you append the parameters. You augment the transformer in that way that you append the parameters. Or you can do parameter composition that you actually change those parameters directly, but in an intelligent way, as we will see now. We will take now an overview, don't get scared, of the 3 architectures. You can see in pinkish violet color, it's the only part that's being trained. Everything else is frozen, right? And we'll start with the function composition with the bottleneck adapter, whose concept is simpler. So we can see the transformer layer, and it just inserts this module, the adapter, after the feed-forward layer, sublayer. It's basically 2 matrices, down projection and up projection matrix, with the intrinsic dimension of around 250. Just to keep that in mind, because it will later be important for this rightmost image. Then we have input composition, whose representative would be prefix tuning. And here you append, as mentioned, parameters. You append them to keys and values, not the key and value matrices, but the keys and values directly before they go into the self-attention sublayer. And the third one is parameter composition, which is like low-rank adaptation. To the rightmost, you can see 2 matrices. The yellow one is like the original weight that you have, and the pink one is what you have changed. You have added this like parallel connection, and the pink ones are the only weights that are being changed. The idea is that it's been found that transformers, since they're so complex, that actually there is an intrinsic lower dimension. And by intrinsic lower dimension, I mean this thing in the middle. So it's 2 matrices, like, again, down projection and up projection, but this time a lower intrinsic dimension would be like 5. So you can imagine that it's much less parameters on the right in pink than on the left in the original matrix. And that's what they do with query and value matrices in the self-attention sublayer. And here you now have 3 options. What are the benefits of the one, what are the benefits of the other, which one would I choose in my use case? And now we'll go into some of the benefits and drawbacks of each of them. Well, it depends on what you're looking for. If you're looking for the first column, which is parameter efficiency, which means, okay, I want as least as possible parameters, then the function composition, which is here, the leftmost, is not the best. I said the intrinsic dimension is 250 approximately. Then you have parameter efficiency for parameter composition. That would be rightmost. And this is a bit better because the intrinsic dimension is like 5. So you have less parameters. But the least parameters that you add is this prefix tuning. And this adds, it only appends the parameters. Since you're appending, it's much less than actually having the matrices. Okay, but what if you want your training to be as efficient as possible? Maybe you need to train your models as fast as possible. Then, okay, function composition is fine with this. It is slower because you have this additional serial thing, but you train much less parameters, right, than the single task learning. Well, the problem with input composition is now the largest. Why? Because self-attention mechanisms scales in time, like quadratically with input size. So here you're actually increasing the input of things that go into self-attention mechanism. Why? You're adding task-specific things, so you can put attention on those, and the model can extract the knowledge for the specific task, but you're basically extending the input. Well, that means that the training will also be longer. What will also be longer? The inference, right? So it's a problem. And parameter composition, here it says it's bad because also sparse subnetworks with few iterations come into parameter composition, but this representative LoRa does not have this problem. It's very similar to function composition. But maybe you want your inference to be as fast as possible. As mentioned, input composition is not good here because it extends the self-attention, and that's why it lasts longer. But parameter composition, for example, is very efficient. Why? Because during inference on the right, you can basically merge those weights. Okay, during training they need to be separate, but during inference they come like as one, and that means that the inference for single task learning and for parameter composition of adapters is the same. Well, in terms of performance, well, it seems that if you had the most parameters, maybe like function composition, then maybe the performance is slightly better than our other approaches. Parameter composition maybe lags a little bit behind, but you can again increase this intrinsic dimension on the right. Maybe you get a bit more parameters, but you also get like a bit more complexity to train and learn your task. And input composition seems to again lag behind a little bit. The good thing is that they're all compositional. You can trade them, share them, and somebody else can download them and do the same thing. And then maybe you're wondering, some of these perform better on one type of tasks and one type of domains, some of them perform better on the other. So there's also some combinations. You can, instead of trying all of them for all the tasks and all the combinations, you just let the end-to-end backpropagation decide it for you. You introduce these new gates, and the gates basically tell you, okay, for this batch, for this task, for this example, LoRa is more important, or prefix tuning. So it basically just weights it for you instead of you doing it manually. Also, maybe you've trained your adapters and now you want to use the knowledge. Let's say you've trained 3 of them, and for 3 different tasks or 3 different domains, and now you want to train a 4th one, but not adapters. You want to use, not the new adapter, you want to use the previous ones that you had trained. Then you can do diffusion. So basically, again, you let the model decide, okay, how much does each of the adapters contribute to this example or this batch or this task. You have your queries key values, like similar to the attention mechanism. You do the dot product with the query and keys. You do the softmax, basically get like the weights, how important which of the adapters is, and then you weight the values to give the contribution to each of the values. Yeah, and the problem with adapters, as you can see, besides this last adapter fusion, which is a bit more hefty, it does bring you a larger inference time, is that you're not sharing anything. And that's why the hypernetworks came into play. Those are basically the networks that generate the parameters of the other network. And the idea is to have this hypernetwork, which will be shared, so the knowledge is shared, but also to have the task-specific components that are actually generated through this shared hypernetwork. And so you have like the best of both worlds, like the shared encoder, you're sharing the weights, and like the adapter, you get task-specific components, but in a smarter way. And the architecture, again in blue, we have the component that's being updated by all the tasks. in green, we have the component that's updated by just the current task that you're training. That's in this batch, for example, and the Hypernetwork, based on its parameters and based on the embedding that it's given, generates the model parameters, which are then used in, for example, forward pass. And for the actual example, now, like, follow me a little bit. On the right, component number 3 is like transformer layer, right? We've seen it previously. Component number 2 on the right is the adapter, bottleneck adapter, which we had also seen previously. It has this feed-forward down projection, up projection. But on the left, component number 1, we have the Hypernetwork. And now we'll start from the component number 1, Hypernetwork, but from the bottom, which is like the beginning. We have, as previously we had a task embedding, now we also can add a language embedding. The task embedding, it's intuitive. You have this task and you use this embedding just when you're training this task. But maybe you have the same task, but in few languages. Then you can use specific language embeddings as well, which you switch. And the layer embedding is here so that, for example, let's say you have 12 layers in an encoder, so that you don't have a separate hypernetwork in each layer. You just instead add a layer embedding, which is much, much, much less parameters than having a separate hypernetwork. So that's the goal, have at least as possible parameters and obtain the same performance and even better. Then this gets concatenated and pushed through this hypernetwork in blue on the left. It's again like a multi-layer perceptron, nothing special, some down projections and up projections, and it spits out the parameter vector that is of a defined shape, always the same shape that you know that you will need, because it then gets reshaped into this adapter that we mentioned previously. So now we're generating parameters and we're reshaping it into an adapter instead of having a separate adapter for everything. And then this adapter gets used in like a forward pass, and in the backward pass you go all the way back to the embeddings. So the hypernetwork gets updated, and all the task and language and layer embedding also gets updated with the backprop. It's the beauty of training this end to end, even though you have this proxy. And you can see that again you have some shared weights. You might experience similar problems like with the shared encoder, but the thing is that here you're not directly using those shared weights. It's like a proxy, and additionally it has the input embedding, which then, based on it, it generates new components whose components are actually, whose weights you're actually using. So as mentioned, you might experience similar problems. They're all here, they're all the same, but in much smaller measure, and sometimes even ignorable. So the interference you can imagine is still here. You have this one hypernetwork that all the tasks are updating. They might fight for the gradients going this direction, that direction. Problems with sampling and loss weighting, as mentioned previously. More sophisticated methods, but maybe you could be fine with just something just simpler. And underfitting and overfitting on larger or smaller data sets. These are all problems that make sense because you're sharing the weights, but empirically, they're just so smaller. You don't get those problems that much in practice. And let's see what our friend ChatGPT thinks about multitask learning, because doing one thing at a time is so last year, as he thinks. And I mean, it was not even here last year, so what is it? No, yeah. With that being said, I thank you for your attention, and in case there are any questions, of course, we can spark some discussion.
So my question would be, if I wanted to add a task after I've already trained the model, I want to use all the tasks that it already has memorized, And I want to add another one. Is there a chance I could do that without really losing much of its performance on the previous ones?
Yeah, of course. But it depends on what you're doing. If you're using adapters, as I said, they're not sharing anything. So you would just train another adapter because it's so small amount of parameters that are being trained, so it's a bit more efficient. But in case of hypernetworks, what you could do is, okay, you have a currently trained hypernetwork that's generating weights depending on which task embedding you're giving it, which language embedding you're giving it. So you can, it's a bit more heavy to train, it lasts longer because you're introducing this continual learning regularization. But basically you say, okay, I have these weights that are generated previously based on the hypernetwork weights and the other embeddings that I had given it. All the tasks that I had previously trained, I give all the embeddings. And you save these weights. Then you do the optimizer step, for example, and you take a look at the weights afterwards. How much had they changed? But not the weights of the hypernetwork, because you don't care actually about this. You take a look at the weights that had been generated by the hypernetwork that the actually previous task will use directly, right? Those are the ones that are important. And you just take a look at the difference. You can like subtract it, power to sum, and you add this as another loss term, additional loss term. And then you have this hypernetwork of how much do you want to put emphasis on learning new tasks, and how much do you want to put emphasis on not forgetting previous ones. And you will have this hyperparameter if you want to weight the loss of the continual learning regularization more, or you want to weight it less. There will be some forgetting still. It's not perfect, right? You can, again, the problem is with introducing, for example, I don't know, Fisher matrix, that takes into account the actual gradients from before. Well, you're not working with direct weights. You're working with something that has been generated. That's what's important for you. So you have a bit of trouble with getting those gradients. But yes, it would be possible. It's not perfect. There is some forgetting either, or the new task will be trained with a bit smaller performance, or it will converge slower. It depends on the, yeah.
Okay. Follow-up question. Would then adapters be a better solution, maybe, if we really want to try to keep all the knowledge we had before and just add some new knowledge?
Again, it depends, because, for example, hypernetworks tend to converge faster. You are sharing the weights, and you somehow get these good gradient updates from those, and proxy weight sharing. So yeah, you could reach a higher performance here, but then in terms of learning a new task, you again lose some. With just pure adapters, you don't have so much trouble with adding a new task continuously.
Thank you.
Okay, I have a more general question about this ChatGPT. Do you think that since it took, as we heard, a record number of customers in his beginning of users, do you think that ChatGPT is going to become like Facebook of these AI models, meaning that it will take 90% of market? Or is there room for some competition? Or is there going to be some disruptor like Snapchat for Facebook?
Yeah, I think their strategy is just to go very, very aggressive. Maybe they could even be making some losses, depends, maybe they're waiting for investors, because if Google did that with its Google search with so many customers, if it did like ChatGPT run every time somebody ran a Google search, it would just cost too much, right? So the OpenAI can currently do that. They can do this like aggressive tactics because Bing, I don't know, has less users. So it's a big game of big players. They're keeping it all closed source, which is, yeah, good for them, not good for everybody else. And they've benefited the most from the open source thing. So it's also funny. It's really hard to say if they will become new Snapchat. We need to keep in mind that there also had been and will be AI winters, which is like one part of the history. So what they're trying to build is something very general that has like cognitive capabilities, but maybe currently these are just stochastic parrots because they're getting better and better when you feed it more and more data, like, I don't know, cognitive system maybe would not get better when it has more data. So this maybe means that it's just replicated what it had seen. And additionally, if it wants to do something like innovative that it hadn't seen, if you prompt it that way, it will try to, I mean, it will not try, but it will hallucinate. It will go into different directions. Mostly it will just be wrong because it doesn't have cognitive capabilities. It's just like probabilistic. Oh, I've seen this word that many times. And I'll maybe go in this direction. And it's like generating word by word. So I think there are actually better architectures to come than the transformer for this thing that they're trying to build, like the cognitive general intelligence and whatever.
Thank you. If that is it. Okay. Here. Bravo. Evo može ovo.